Hello, hello friends. So last video we have seen what is flexibility method and what are the some basic knowledge regarding flexibility method we have seen. Now in today's video we'll see one small example how to analyze a particular beam with a flexibility method. See here I have taken this particular example. So here one beam is given, ABC beam is given, and the external loading is also given as one UDL, and next one is a point load. So for this, as far as flexibility method is concerned, this particular method is called as a force method, so that we have to find out SDI value, that is static degree of indeterminacy, for this particular problem. So first step itself we have to find out SDI value. How to calculate SDI value? Simple formula, R minus E. R is your support reactions and here E is equilibrium equations. So in this particular problem we have 5 reactions, 3 equilibrium equations. That means SDI value comes out to be 2. So we have to assume two forces as a redundant forces. Let us assume RB and RC as a redundants over this. Okay. In next problem, in second step, you have to draw M by EI diagram. That is moment bending moment diagram. So in this regard, we have assumed two redundants RB and RC. Let us say B point. Let us assume B point as a node 1 and C point as a node 2. Okay, so in second step we have drawn this particular M by EI diagram. First we will draw M by EI diagram for UDL, which is over on AB span of magnitude 10 kN per meter. So due to UDL, the bending moment diagram, or say bending moment at point A, will be equals to 10 into 3, that is your magnitude, into your half of your span, that will be your moment. So that will comes out to be 45 by EI, and that will be acting at A point, which is in a negative direction. That means this particular moment will be in a hogging bending moment. Okay, so from this you can easily calculate this first M by EI diagram due to first external loading. From this you will have to develop your delta L matrix, which is delta L matrix means displacement due to external loadings. Okay, so here you have two external load. First we have drawn for UDL. Now next is your point load, which is at 2 meter distance from B point for span BC. So due to this point load, you can see over here at point A bending moment will be comes out to be 20 into 5, that is 100 by EI, and for at point B that will be equals to 40 by EI, 20 into 2, 40 by EI. Okay, you can draw this M by EI diagram easily with the help of your external loading which is applied on the structure. Okay, now how to develop this delta L matrix? See here, delta L matrix will be nothing but a column matrix depending on the number of redundants. So here two redundants are there. That means this will be column matrix having two elements, that is delta 1 L, delta 2 L. Now what is meant by delta 1 L and delta 2 L? So here delta 1 stands for node value, okay, and L stands for loading, due to loading. Okay, so delta 1 L, it is the displacement at node 1 due to external loading. Okay, we have two external loads. For these two external loads we have drawn M by EI diagram as well. So you have to find out only the displacement at node 1. In figure also you can see over here joint B is treated as a node 1 and joint C is treated as a node 2. So what is displacement now? Delta, that means displacement. How to find out at node 1 the displacement? Okay, that is nothing but you have seen in consistent deformation method. Okay, if you are interested in slope, you have to find out only the area of your M by EI diagram, and if you are interested in displacement, so in that case you have to find out moment of your area of M by EI diagram. So here two diagrams are there, M by EI diagram. Due to first your UDL, we have drawn a parabolic curve. So due to parabola, how to find out this delta 1L, you can see over here will be equals to minus 1/3. Why it is minus? Because it's a Hawking bending moment. 1/3 into base into height. 1/3 into base is 3 into height is 45 by EI. It has to be EI. Okay. Into 3/4 of 3. That means we have to consider only moment of this area of M by I diagram. But that particular moment is with reference to node 1 only. So that means you have to find out the distance from node 1. So that will be equals to simply 3/4 of your base, that is 3. Okay. Next delta 1L will contribute from this second diagram due to point load on span BC. So here you can see a triangle shown is here, but you are interested only displacement at node 1. Okay, node 1 is at point B. So you can go either for left part or right part. Okay, for first delta 1L due to first loading, you have seen only left part you are considering. So therefore, for second diagram also you have to consider only left part of your section, that is left part of your node 1. So if you look at left part of your section will be a trapezoidal of say different heights, say from 40 by EI to 100 by EI. So you have to find out moment of this area, trapezoidal area, about 0.1 or say about node 1 only. So how to find out? Let us divide this particular trapezoidal area into two parts. First one is a rectangle, next one is a triangle. So first part is rectangle. How to find out moment of this rectangle area? It is nothing but the only length into breadth, that is 40 by EI into 3 into half of your distance from node 1, that is half of 3. So here we have written 40 by EI into 3 into 3 by 2. Once again it is a minus because this particular moment will be a Hawking bending moment. Okay, next we have remained the second part of your trapezoidal, that is 100 minus 40, that is 60 by EI. The height of this triangle is 60 by EI. So area of triangle is half into base into height, half into 60 by EI into height base is 3. Okay, into once again 2/3 of 3, that is we are interested to find out the displacement at node 1 only. Okay, so if you add these three values you will get delta 1L. Okay, if you add these three values you will get delta 1L, that will comes out to be minus 461.25 divided by EI. Next is delta 2L, that means displacement at node 2 due to your external loading. Once again we will discuss how to find out this delta 2L. Now we are interested delta or say displacement at node 2. That means you have to find out you have to measure your distances of your area has to be measured from node 2 only. Okay, so first if you are targeting first parabola, the area of parabola is 1/3 into base into height. Now distance of your center, okay, distance of your say parabolic center from node 2 you have to calculate. That means 3/4 of 3 plus this 3 BC span. Okay, so that will be your first say moment of area. Next we have a triangle due to your point load. So from triangle you can easily calculate half into base into height, and the center of this will be 2/3 of base from D point, but you are interested from node 2 which is joint C. So that has to be added 1 meter. 1 meter has to be added in this. So you will get delta 2L. If you add these two values will be given to delta 2L. That will comes out to be minus 1319.58 divided by A. Once again these two both the values has to be minus because both bending moment will be Hawking bending moment. Okay, so next we have to draw. Let us go for third step. Now for third step you have to draw M by A diagram once again, but due to by applying unit force in the assumed direction of your redundants, and you have to form your flexibility matrix. Now here see, you have decided RB and RC as a redundants. So you have to apply unit force in the assumed direction of your redundants. So let us say first you have to apply a unit force in the assumed direction of your first redundant. Let us say RB is the first redundant, first node, right? So we have applied here 1 kilonewton force in the assumed direction of RB, that is in upward direction, and you have to draw M by I diagram with the help of this force. So if you apply one or say unit force at point B, you have to draw M by I diagram. That will be a simpler triangle, will be having a height as a 3 by EI. Okay, and then if you apply unit force in the assumed direction of second redundant, that is RC, you will have to apply here 1 kilonewton. You can see over in second diagram, second figure, 1 kilonewton is applied on RC in the assumed direction of RC. So you will have one triangle of having ordinate 6 by EI at A point and 3 by EI at B point. So now with the help of these two figures you have to find out flexibility matrix. So for flexibility matrix we have seen this is, we have assumed only two redundants over here. That means this particular matrix will be having square matrix having 2 by 2 ordinates. So that will be having only 4 coefficients, 4 elements. How you will calculate? Let us say F11, F12, F21 and F22. Now how you will calculate this one? Let us say first F11. F11 is nothing but the displacement produced at node 1. First one stands for displacement produced at that particular node. Okay, so F11 is displacement produced at node 1 due to application of unit force in the assumed direction of redundant at node 1 only. Okay, clear? So F11 and F21, these two values will be you are getting from first figure, because F11 or say F21, that is nothing but displacement produced at node 1 and node 2, but due to application of unit force in the assumed direction of redundant at node 1 only. So that means if you apply unit force in the direction of RB, then and then only you can have these two values F11 and F21, right? So now F11 is displacement produced at node 1. That means you are interested in measuring the distance from node 1 only, and F21 it is nothing but the displacement produced at node 2. That means you are interested to find out the measurement distance from node 2 only. So here if you try to figure first diagram, here F11 is nothing but half into base into height, which is your triangle, half into 3 by EI into 3 into your distance from node 1 only, that is central distance from node 1, that means 2/3 of 3 only. That will give you F11 value, and that will be comes out to be 9 by EI. Okay, if you go on F21 is nothing but you have to check only first figure only, because now we have to apply unit force in the direction of redundant at node 1 only. So here now we are interested in measuring the distance from node 2. So that means the area of triangle will remain same, half into base into height into 2/3 of 3 no doubt, but we have to measure this distance from node 2. That means 3 has to be added in that is span of BC. So that is 2/3 of 3 plus 3. So that will comes out to be 22.5 by EA. So that is F21. Now F12 and F22, how you will calculate this one? So second F12 or F22, that means displacement produced at node 1 at node 2, but due to the application of unit force in the assumed direction of redundant at node 2, that means if you apply unit force in the assumed direction of RC, that will be your displacement produced at node 1 and node 2, F12 and F22. So here F12 is nothing but displacement produced at node 1. So you have to find out, you have to measure the distance from node 1 itself. So you can see over in this second figure, second triangle, in this you are interested only measurement from node 1. That means once again you have to check only left portion of your node 1. So if you figure out left portion, you will see a trapezoidal having ordinates, two different ordinates as 6 by EI and 3 by EI. So you have to find out the area of this triangle, so trapezoidal, and you have to find out the area of this moment of this area. So once again you will divide this trapezoidal into two parts. One is a rectangle, next one is a triangle. So first rectangle is having area as 3 by EI into 3 into your half of your distance, central distance, that is 3 by 2. So here you can see 3 by EI into 3 by 2 is my first rectangle part, and then next is the remaining triangle. So once again area of triangle is half into base into height. You will find into your central distance measured from node 1 itself. So that means half into base into height into 2/3 of your base, 2/3 of 3. So if you add these two values, you will get F12, that will be 22.5 by EI. Just reminding, these two values are your non-diagonal values, F12 and F21. That has to be same itself. Okay, then and then only you can proceed further. So this will be a check for all of you. F12 and F21 has to be equal. Now next is F22. How you will calculate F22? So F22 is nothing but your area, moment of area, that is displacement produced at node 2 due to application of unit force in the assumed direction of redundant at node 2 itself. That means simple, you have to take area of this triangle, say in figure 2 only, area of triangle, that is half into 6 by EI into 6 into central distance measured from 2 second node. So 2/3 of 6, it will be comes out to be 72 by EI. So here all the four elements we have calculated. Now if we continue, there will be, you can see over here, F matrix, that is called as a flexibility matrix. 1 by EI is taken as common outside of your matrix into your elements 9, 22.5, 22.5 and 72. And next you have to find out inverse of this matrix. How to find out inverse of matrix? It is nothing but simply 1 by determinant of your matrix into adjoint matrix. So 1 into determinant, how you will calculate determinant? You have to multiply your diagonal elements minus multiplication of your non-diagonal elements. So that means 9 into 72 minus 22.5 square. That will be your determinant. That will comes out to be 141.75. Okay. So this is your determinant value. And how to find out now adjoint matrix? Adjoint matrix, how to find out? So for 2 by 2 matrix, you can find out adjoint matrix easily. You have to simply replace your diagonal elements, that is 9 will be replaced by 72 and 72 is replaced by 9. So only you have to replace these two elements, and you have to change the sign of your non-diagonal elements. So that means 22.5 will becomes now minus 22.5. So that is your adjoint matrix. Both non-diagonal elements has to change their sign. So now this will be your adjoint matrix. And now F inverse is nothing but simply you have to take the division here, 72 by 141.75 will becomes out to be 0.508. Next one is minus 0.159. Next is 9 divided by 141, that is comes out to be plus 0.064. So this will comprise of your F inverse. So inverse of your flexibility matrix. Now you have to use your compatibility equation which is your R is equals to F inverse into delta minus delta L matrix. So where R is your redundant matrix, we have chosen two redundants, that is RB and RC. So this will be a columnar matrix. Next one is a delta matrix. Delta is your displacement matrix, which is called as a given displacement matrix. There is no any displacement is given in problem itself. That means there is no settlement is given in problem itself. So this will be a null matrix, zero matrix, but it will be a columnar matrix only. And next one is the delta L matrix. We have just calculated in step number 2 what is delta L matrix. Delta 1L, that is displacement, joint displacement due to external loadings. We have just calculated these two values, delta 1L and delta 2L. And the final is F inverse. You have just calculated in step number 3. Now you have to rearrange, or say you have to replace all the terms in your compatibility equation. So compatibility equation will becomes now RBRC, that is R matrix, will be equals to EI into F inverse matrix into, now here delta is null matrix and delta L comprises of both the values are negative. So minus minus will becomes now plus. So here you can see this will be a plus values. Two values are, both values are plus value, 461.25 and 1319.58. So here this will be your equation, compatibility equation. Now from this equation you have to calculate RB and RC. You can just you can take multiplication of these two matrices. How you will take multiplication? Only the simply first element 0.508 into your first element of your column matrix, that is 461.25, plus your second element, that is F21, that is minus 0.159 into your second element of your column matrix, that is 1319.58. So if you add these two values, you will get your RB value as 24.502 kilonewton, which is our redundant force, right? So similarly you can find out RC value. RC is nothing but your first element, that is F12 minus 0.159 into your first element of column matrix, that is 461.25, plus second element of your say last element of your flexibility matrix, that is 0.06564 into your second element of your column matrix, that is 1319.58. If you add these two values, you will get your second redundant value, that is 11.114 kilonewton. So that means the unknown terms, or say two unknown terms, or say two redundants, which are excess in your equilibrium equations that you have just calculated, RB and RC. Now next step, you have to find out the other support reactions. How you will find other support reaction? Just you have to use your equilibrium equations. Let us say summation of Fy we have taken. What is summation of Fy? Simply Ra plus Rb plus Rc will be equals to 0. That will be a summation of Fy. Rb and Rc you have just calculated. You know all the vertical forces. From this you can find out Ra value. Okay, and then summation of moment about point A has to be equal to 0. So for this you can see Ma you can easily calculate. Okay, we have taken Ma as say Hawking bending moment. That's why you can see over here minus Ma plus total loading. We have to calculate the moments, and then due to support actions Rb and Rc, because we are trying to find out summation of moment at point A only. So from this you can find out Ma value, which will be comes out to be 4.81, and Ra comes out to be 14.384. And the next one, you are interested in MB also. How to calculate MB? Just consider a separate span of AB, separate span MA and MB plus just taken as a Hawking bending moment we will consider due to UDL and of 3 meter span. If you consider summation of moment about point B will be equals to 0, then you will get this equation will be equals to minus Ma plus MB minus, because it's once again a anti-clockwise direction moment, 10 into 3 into 1.5 plus due to Ra the moment will be in a clockwise direction, that is plus value 3 into Ra. So from this this equation you can easily find out MB. That means all other support reactions we have just calculated as Ra, Ma and MB. Now the just remaining part is to draw SFD and BMD. So for BMD you have to find out free span moments. That means individual span you will consider with the help of as a simply supported span. So for span AB, bending moment maximum will be at center will be equals to WL square by 8 and will becomes out to be 11.25 for span AB. Now for span BC, bending moment will be at the point D itself where the point load is acting. So that value will be equals to WAB by L, and that will be comes out to be 13.33. Okay, so here this will end your free span moment. And the final, now we have to draw SFD and BMD. You can draw easily SFD BMD. See here for SFD, RA is in upward direction. RA value is 14.384. So if you take section just right of your A point, if you consider only left portion of your section, you'll find one force which is in upward direction, so it has to be plus 14.384. Then due to UDL, 10 into 3, that is 30, has to be deducted from this, which will be comes out to be minus 15.616 at point B, just left of your B point. Okay, and if you goes on section on just right of your B point, then you have to add RB value. It's in this particular value. So RB will be your 14 point, sorry, RB will be your 24.502. If you add this one, this will be comes out to be 8.886, which will be positive direction, positive value. So this value will remains until your point force is coming. So this will remains constant up to point D, and then due to point load, once again it will be deducted by 20 value, and it will be comes out to be 11.114, which will be constant up to point C, and then RC will be added as 11.114. So yeah, the final value will be 0. So this will be your SFD. And bending moment diagram, you have to just draw first free span moment as a positive values of bending moment diagram. Here you can see for AB span we have drawn a parabolic curve of maximum ordinate as 11.25, and then we have drawn a triangle for BC span, that is having maximum height as 13.33 at D point only. Okay, so these two values are positive values. That means these two values are sagging bending moment. Now we have to superimpose the hogging bending moment over this. So that means negative value has to be superimposed in this. So we have just calculated MA and MB are both are positive. That means we have assumed a perfect direction for this. That means MA and MB are both are in hogging nature. So 4.81, that is MA value, we have taken as a minus. We are superimposing. Therefore this value will be in upward direction, or say positive direction of your datum line, reference line. And then MB also is also a hogging bending moment. It is also drawn in on a positive direction. So if you join these three values, we know that moment at point C will be 0 because it is a simply supported end. Okay, so you have to join these three ordinates as a simple straight lines. Now you can see this particular area will be a positive area, and these two values are negative areas, and the remaining areas are just cancelled with each other. Okay, I guess you are understanding this, all this term. If any doubts are there, then you can clarify, you can ask me at any time. Okay, thank you. In next video we will see what is stiffness method, okay, which will be called as a displacement method. Okay, if any doubts you can ask. Thank you.